Professor Dave and Chegg here. It's time to begin to understand certain properties that solutions will display, because the behavior of a solution will be different from the behavior of a pure solvent or solute. This will be most evident during phase changes, as solute particles will interfere with the way that a solvent undergoes a phase change. Let's start by looking at the vapor pressure of a solution. As we know, a pure liquid will have a certain vapor pressure, boiling point, and freezing point. But once solute is added to this liquid, generating a solution, the physical processes that are related to these values will experience interference from the solute particles. As solvent molecules attempt to go from the liquid phase up into the gas phase, or as they attempt to go into the solid phase by forming a lattice, the solute particles will obstruct this behavior, resulting in an alteration of vapor pressure, freezing point, and boiling point. Specifically, fewer particles will vaporize, resulting in a reduced vapor pressure. It will be harder to boil, resulting in an elevated boiling point, and it will be harder to freeze, resulting in a lower freezing point. These properties that are exhibited by solutions are called colligative properties. They involve the properties exhibited by a solution by virtue of solute particles that interfere with physical processes that the solvent can undergo, like phase changes. And unlike other properties of solutions like acidity and basicity, density, or viscosity, which will depend on the identity of the solute, colligative properties do not depend on the identity of the solute, merely on the concentration of the solute. Let's now get quantitative with each of these colligative properties. The first property we will examine is vapor pressure lowering. As we know, a liquid will always exhibit some equilibrium between the liquid and gas phase, as some particles will be escaping the liquid to enter the gas phase, and some particles in the gas phase will collide with and re-enter the liquid phase. This equilibrium is what determines the vapor pressure of a liquid, which has to do with the number of gaseous particles there will be at a given temperature. The vapor pressure will depend largely on the surface area of the liquid, because only particles at the surface of the liquid will be able to vaporize. This is why, if some non-volatile solute is added to this liquid to form a solution, the vapor pressure will be lowered. Solute particles will occupy some of the locations at the surface of the solution and will thereby slightly obstruct the ability of some particles to vaporize. If the rate of vaporization is reduced, there will be slightly fewer particles in the gas phase at any given time, resulting in a slightly reduced vapor pressure. This is why there are fewer particles in the gas phase now that solute is present. The relationship between vapor pressure of a substance and its concentration in solution is described by Raoult's law. This states that the partial pressure of any component of an ideal solution is equal to the vapor pressure of the pure component multiplied by its mole fraction in solution. For example, if we have 5 grams of urea and 0.1 kilograms of water, and the vapor pressure of pure water at 25 degrees Celsius is 23.7 torr, what will be the vapor pressure of this solution? Well, we have to get the mole fraction of water, which we can get by calculating the moles of urea and the moles of water. Once we calculate those values, we simply divide the moles of water by the total moles to get the mole fraction of water, which is very close to 1 since the solution is predominantly solvent. Once we have the mole fraction of water, we can plug that in along with the normal vapor pressure of pure water, and we can solve for the vapor pressure of this solution, which will be slightly lowered due to the presence of solute. Now we understand how the vapor pressure of a solution differs from that of pure solvent. Let's check out some other colligative properties. Professor Dave for Chegg. See you next time.